You know the exact feeling, right? It is pouring rain, or maybe you just walked out of a massive concert venue with, I don't know, 10,000 other people.
Oh, yeah, everyone is exhausted.
Exactly. You pull out your phone, you open up your rideshare app, and there it is just staring right back at you.
Yeah.
A massive price multiplier, like 3.2x or 4.5x, maybe even higher.
And your heart just drops.
Right. And in that moment, as you were standing there staring at your screen, feeling this mix of, dread and outrage, you probably wonder what exact mathematical gymnastics triggered this specific number right here, right now.
Yeah, it is a moment of pure frustration for most people, but, from an engineering standpoint, it is a moment of incredible complexity. When you are looking at that multiplier on your screen, you are actually looking at the tip of a very, very deep mathematical iceberg.
Wow. Okay.
Yeah, I mean, it represents a massive real-time calculation that is basically attempting to solve a nearly impossible physics and economics problem.
And that is exactly the mission of our deep dive today. We were taking a really comprehensive look under the hood of Uber's infamous surge pricing model.
We really are getting into the weeds on this one.
We are. We are going to explore the raw engineering, the microeconomics, and the machine learning that actually makes it tick. Because our goal here is to show you that this isn't just a random price hike designed by some guy in a control room flipping a greed switch.
Right, there is no greed dial, they just turn up.
Exactly. It is actually a hyper-complex, real-time engine trying to balance heavy mathematics, physical geography, and, well, the sheer chaos of human psychology.
And the core dilemma we are looking at here is a classic two-sided marketplace problem. I mean, when demand in a specific physical zone vastly outstrips the available supply of drivers, the platform is forced to intervene.
They literally have to step in.
They do. Because if they don't, the entire system breaks down structurally. Wait times would explode to hours, the app becomes functionally unusable, and nobody gets a ride anyway. So the multiplier is essentially their mechanism for intervention.
Which makes sense. But what is genuinely wild to me, looking at how this technology has evolved over the source material we pulled, is just how granular it has become.
Oh, it is completely different now.
Right. Because if you go back to, say, before 2017, this was largely a static rush hour pricing model. You knew that at 5 p.m. on a Friday, downtown was going to be more expensive. It was a blunt instrument.
Yeah, very predictable, very static.
But today, it operates on a completely dynamic minute-by-minute basis. We were talking about calculations running per hexagon per 5-minute intervals across the entire globe.
Yeah, and that transition from a static model to a fully dynamic one requires an entirely different universe of computing. But before we can even begin to understand the machine learning algorithms running this architecture, we really have to start with the pure economic theory driving the code.
The baseline math.
Exactly. The algorithm is essentially trying to digitally manifest a core economic principle.
Okay, let's unpack this, because the economic engine here is doing something very specific with that multiplier to both sides of the market simultaneously.
Yeah, so when that surge price goes up, it is engineered to achieve two immediate effects. First, on the writer's side, it forces a portion of the user base to naturally filter themselves out.
Like, they just give up.
Right. A user sees the 3.0x price, and they make a quick economic calculation in their head. They decide to delay their trip, or maybe they walk to the subway, or they just, cancel their plans altogether. So demand immediately drops.
Which is the part we all feel, right? We feel like we are being actively priced out.
And we feel it because it is actively designed to limit our participation based on our willingness to pay. What's fascinating here is the second effect, which happens on the driver side.
Okay, what happens there?
That higher potential earning acts as a beacon. Drivers log onto the app from their couches, or they start physically driving toward that high demand area. So supply actively increases. The ultimate goal of the entire system is to find what economists call the market clearing equilibrium.
Market clearing equilibrium.
Okay. Yeah, that is the exact mathematical price point where the supply of incoming drivers perfectly matches the remaining filtered down demand from riders.
Okay, so it's like a thermostat. But instead of adjusting hot and cold air to find the right temperature, it's adjusting human behavior using two separate dials.
That is a great way to put it.
Right, so it is pricing out the riders on one side and luring in the drivers on the other, turning those dials until the room is perfectly comfortable, or in this case, until the exact number of cars matches the exact number of people who still want a ride.
That is a brilliant way to visualize it. And the fascinating part is how they map that exact feeling into an exponential mathematical function. To find that equilibrium, the system has to model human behavior mathematically.
Which sounds impossible. Humans are so weird.
We are, but they use something called elasticity curves. They calculate demand elasticity, which is essentially how sensitive you, the rider, are to price.
Right.
So as the price goes up, the number of riders willing to pay doesn't just drop in a straight line, it drops off exponentially.
Because there is a breaking point. I mean, a 1.2x surge might not deter me,
Right.
but a 2.0x makes me pause, and a 4.0x means I am absolutely taking the bus. The sensitivity just accelerates.
Exactly.
And I imagine they have to build an opposing exponential curve for the drivers, right?
They do, yeah, and that is the supply elasticity curve. Like, how motivated are drivers by earnings at any given hour? As the potential payout goes up, the willingness of drivers to get in their cars and get on the road increases exponentially.
Okay, I follow.
So the literal math problem the servers are trying to solve every few seconds is setting those two exponential functions equal to each other and solving for the price. When demand mathematically equals supply, that resulting price is your surge multiplier.
Okay, theoretical math is great. The concept of an algebraic equilibrium makes perfect sense in a microeconomics textbook.
Sure.
But how does that theoretical intersection actually become the 2.5x multiplier on your phone screen in real time? Because there's a massive leap between drawing two crossing lines on a chalkboard and running a piece of software for millions of people.
Oh, absolutely. And this is where we get into the real technical meat of the architecture. The key insight underlying this whole system from our sources is that the surge multiplier is actually something called a dual variable.
A dual variable.
Yeah, which is often referred to in mathematics as a shadow price.
A shadow price. I mean, that sounds like something out of a cyberpunk novel.
Aha, it has a very mysterious name, I agree. But it comes from a very concrete branch of mathematics called linear programming optimization.
Okay.
So imagine you are trying to maximize the overall health of the marketplace. You want to get the absolute most people rides while keeping drivers earning at a steady rate. You have a massive equation representing this goal, but you have a constraint holding you back.
The physical cars.
Exactly, the physical, limited supply of drivers on the road. In linear programming, every constraint has a corresponding dual variable. This variable represents exactly how much better your overall outcome would be if you could just loosen that constraint by one single unit.
Let me see if I follow this. So if you just had one more driver magically appear on the map, the dual variable measures the exact monetary value of the system improving.
You nailed it. That is exactly it. If driver supply is incredibly tight, say, right after a football game ends, that dual variable skyrockets. The math equation is essentially screaming, we desperately need more drivers here, and adding even one more driver is worth a massive premium.
Wow, okay.
And that theoretical dual variable literally becomes the surge multiplier pushing the price higher. On the flip side, if supply is plentiful and there are drivers idling everywhere, that dual variable drops to zero.
Because you don't need them.
Right. There is no constraint on the system, so the shadow price is zero and there is no surge.
Wait, hold on. Let me push back on the logistics of this.
Sure.
Are you saying they are running a mathematically perfect, citywide, linear programming optimization, calculating every single rider, driver, and route constraint every single second? Because just thinking about the sheer computing power required to constantly solve an equation with millions of variables, there's no way. They must be taking a shortcut. Are they just running a localized, dumbed-down version of it on the fly?
Your intuition is spot on. Running a continuous, citywide, linear programming model at that scale every second is computationally impossible.
It would literally melt the servers.
It absolutely would. It is way too heavy for real-time production. So instead of solving the massive math problem from scratch every second, production systems use a machine learning approximation.
Okay.
The ML model looks at a very specific localized ratio. It looks at the number of active rider requests divided by the number of available drivers within a certain radius.
So they bypass the massive equation entirely and just look at a proxy metric.
Yes, exactly. They take that localized supply and demand ratio and map it to a multiplier based on historical data. This ratio model essentially mimics the behavior of that theoretical dual variable we just talked about.
That is so clever.
It acts as an amortized approximation of the shadow price. It gets you the benefit of the deep microeconomic math without requiring the impossible computing power.
That makes so much more sense. But math, even machine learning math, still assumes a perfect, frictionless world. I mean, the algorithms assume data flows instantly. But the real world has hard boundaries.
Very hard boundaries, yeah.
It has traffic jams, it has rivers dividing cities, and it has physical distance. How do they actually map this fluid math onto static, physical city streets?
Well, they have to break the physical world down into manageable, quantized pieces. Cities are not treated as single, giant entities by the algorithm. Instead, they are chopped up into what is called the H3 system.
A3 system.
Yeah, this is an incredibly precise grid of hexagons layered over the entire globe.
So it's less like a digital board game and more like a massive cellular network. Just like a phone call is handed off from one cell tower to the next without dropping, the algorithm must be constantly handing off driver supply data from one hexagon to the next to keep the transportation network connected.
That is a perfect analogy, yeah. The algorithm evaluates the supply and demand within each of those specific hexagons in distinct 5-minute time slots.
Only 5 minutes.
Just 5 minutes. The machine learning models take that real-time ratio of riders to drivers in that specific cell, but they also feed in historical data, current weather conditions, and whether there are any major events happening nearby.
So it's hyperlocal.
Exactly.
Wow.
All of those real-world factors dynamically adjust the elasticity curves for that one single hexagon.
Okay, here's where it gets really interesting to me, specifically thinking about the geography of this.
Yeah.
Let's say one hexagon, say, the one covering a downtown stadium, is surging at 3.0x.
Okay.
But the hexagon right across the street, just a few blocks over, is sitting at the baseline 1.0x. If I am a driver looking at my map, I am absolutely going to step on the gas and cross that invisible border to get the higher fare.
Of course you would.
Right. But doesn't that mass migration instantly create a vacuum in the neighborhood they just left?
You have just identified what engineers consider one of the absolute most difficult challenges in the entire system. They refer to this phenomenon as spatial coupling or boundary effects.
Because the drivers aren't static data points. They are self-interested agents moving based on the mathematical incentives provided to them.
Exactly. If we connect this to the bigger picture, if all the drivers in the 1.0x hexagon rush across the invisible line into the 3.0x hexagon, they leave their original neighborhood completely empty.
Right.
They break the connectivity of the overall network. So now, suddenly, the empty neighborhood has zero supply, which causes a brand new, violent surge to spike over there.
And then the drivers look at their app, see the new surge, turn around and rush back. It's like a completely endless wave of cars chasing a moving target.
It creates a massive network-wide oscillation, a geographical pendulum swinging back and forth, which is terrible for riders who can't get a car, and terrible for drivers who are burning gas chasing ghost surges.
Oh man, what a nightmare.
It is. So to prevent this, the engineers use a heavy mathematical technique called graph Laplacian regularization.
Okay, you're definitely going to have to translate that for us.
Yeah?
How does a graph Laplacian stop a stampede of cars?
Fair enough. Think of it as a mathematical penalty that artificially blurs the lines between the hexagons.
Blurs them how?
So the algorithm looks at the adjacency matrix of the map. If it sees a steep gradient like a 4.0x right next to a 1.0x, the regularization kicks in and applies a smoothing penalty. It artificially forces the 1.0x zone up to maybe a 2.0x and pulls the 4.0x down to a 3.0x.
Oh, I see.
Yeah, it mathematically penalizes steep geographic cliffs so that there is a smooth gradient across the city. By removing the extreme border contrast, they remove the incentive for all the drivers to stampede at once.
That is incredibly elegant.
Yeah.
It physically dampens the shock waves across the city grid before they can even form.
Furthermore, they are not just looking at the present moment. They use forecast-aware controls, specifically something called Model Predictive Control, or MPC.
MBC got.
The system doesn't just evaluate the current 5-minute window. It predicts the future state of the grid. If it knows a massive concert is wrapping up at 11:00 p.m., it doesn't wait for thousands of people to open their apps at 11:01.
It gets ahead of it.
Right. It starts slowly raising the surge in that specific hexagon 20 minutes before the crowd even pulls out their phones.
Oh, wow. So by the time you walk out the doors, the drivers are already idling outside because the system anticipated the demand spike and lured them in proactively.
Exactly. And to make sure the experience isn't totally jarring for anyone looking at the app, they use temporal smoothing algorithms. Just like they smooth out the geography, they smooth out the time.
So no sudden spikes.
Right. They cap how much the price can jump minute by minute. You won't see a price go from $10 to $40 in 60 seconds. The algorithm forces it to ramp up smoothly to prevent wild swings that cause panic for riders and chaos for drivers.
Okay, so the engineering is undeniably robust. The geographic cliffs are smoothed out with mathematical penalties, time is forecasted. But at the end of the day, humans are still heavily involved, and humans are, well, highly unpredictable.
We certainly are.
How does a perfectly balanced, logical algorithm handle the chaotic reality of human psychology, and beyond that, the actual business realities of running a massive, public-facing marketplace?
This is where purely mathematical models always struggle. The system has to constantly battle several human-driven chaos factors. The first is what researchers call driver speculation.
Let me guess. Drivers understand how the code works. They know a surge is coming, so they actively game the system.
They absolutely do. Drivers will purposely log off the app, pull over, and park their cars, waiting for the surge multiplier to hit its absolute peak.
Wow.
They are essentially organizing an impromptu strike, withholding their labor to purposefully drive the shadow price up. But by doing this, they artificially delay the supply recovery that the algorithm is desperately trying to achieve.
That is fascinating. The algorithm completely relies on the drivers to react to the price, but the drivers are reacting to the behavior of the algorithm itself. It is a crazy feedback loop of anticipation. What else disrupts the math?
The second major psychological factor is the cancellation cascade.
What is that?
Let's say a surge goes incredibly high, maybe hitting that mathematically perfect market clearing price. The equation is happy, but the raw number is simply too shocking for a human being to accept. Writers see the price and cancel their requests en masse.
Because nobody in their right mind wants to pay $150 to go 10 blocks, no matter what the linear programming model says.
Exactly. The human rejects the math. So demand instantly evaporates. The algorithm sees zero demand, so the surge price immediately crashes to refine the equilibrium.
Oh, and let me guess.
Yeah.
The drivers, who rush to the area expecting a huge payout, see the price crash, get frustrated, and log off, which means supply plummets.
You got it. And then the remaining riders, who are just waiting it out, open their apps again, demand spikes, and the surge shoots right back up to $150.
That is bonkers. It creates another violent oscillation, but this one isn't driven by geography. It is driven entirely by human emotional reactions to the price tag.
This raises an important question, though, right? How do you manage that as a business?
But what does this all mean for the brand itself? Because structurally, mathematically, a 10x surge might clear the market perfectly. But PR-wise, a 10x surge is a total catastrophic disaster. I remember those infamous news headlines about massive price gouging during the 2014 New York winter storms.
Yeah, that was a major turning point. It forces the platform to weigh massive business trade-offs. It is never just about pure math or clearing the market for the next 5 minutes. The platform is constantly balancing short-term revenue against long-term rider retention.
That makes total sense.
Sure, the algorithm can clear the market and make a lot of money on a 10x surge day, but that rider might feel so exploited that they delete the app tomorrow.
They also have to balance driver earnings versus rider affordability. And there are huge equity issues baked in. I mean, is it fair to charge completely different prices to different people simultaneously just because they crossed an invisible hexagon boundary? These are tough realities of dynamic pricing.
They really are. To mitigate the PR disasters and the psychological shock, they implement strict guardrails. They can't let the math run wild. First, there are ARD caps. The system might have a strict 5.0x maximum multiplier, meaning even if the dual variable says it should be 20x, the algorithm is forced to stop at 5.0x.
Good.
Additionally, surges are legally and automatically disabled entirely during natural disasters or states of emergency.
That is just common sense. You can't have a cold, unfeeling market clearing price when people are fleeing a hurricane.
Exactly. Another massive psychological shift happened in 2017 when they introduced upfront pricing.
Oh, I remember this transition.
Yeah.
The app used to literally show you the raw multiplier. You actually had to manually type in 2.5 to confirm you understood you were paying 2.5 times the normal rate.
Yes. That raw psychological shock of the multiplier was causing those massive cancellation cascades we talked about. Upfront pricing hides that multiplier entirely. Now, it just shows you a flat dollar amount. It says, this ride will cost $35.
Which is so much easier to swallow.
The surge math, the dual variables, the H3 hexagons, the Laplacian regularization is all still happening under the hood. But hiding the raw multiplier dramatically improves the psychological acceptance of the price.
It changes the framing. It feels like a normal purchase rather than a punitive penalty. But here's something I keep wondering as we talk through this deeply complex system.
Yeah.
If they want to tweak this algorithm, say they want to test a new smoothing penalty or adjust the elasticity curve for a specific city, how do they actually test it? In normal software development, you just run an A/B test. You give half the users the old code, half the new code, and see who converts. But they can't do that here, can they?
They absolutely cannot run traditional A/B tests. And the reason why is deeply rooted in the physical reality of a two-sided marketplace.
Hmm.
Think about it. If you give writer A lower experimental surge price, but writer B standing right next to them gets the normal higher price, well, writer A is going to book the ride, taking an available driver off the physical map.
Which instantly lowers the supply for writer B.
Exactly. This violates a core principle of statistical testing called the SUTVA assumption.
SUTVA.
Yes, SUTVA stands for the Stable Unit Treatment Value Assumption. It is a fancy way of saying that in a valid experiment, the treatment of one person cannot spill over and affect the outcome of another person.
Ah, I see.
Because writer A and writer B share the same physical pool of drivers in the real world, the actions of the test group actively sabotage the control group. Traditional A/B testing is mathematically invalid in this environment.
The contamination is immediate. So how do they actually test billion-dollar changes to their algorithm?
They have to use something called switchback experiments. Instead of splitting individual users into test and control groups, they alternate the entire system across time.
Oh, okay.
They will turn the new experimental surge logic on for an entire zone, say all of Manhattan, for a 30-minute block. Everyone in Manhattan gets the new algorithm. Then, for the next 30 minutes, they switch the entire zone back to the old logic.
So the entire hexagon, or the entire city, becomes the test subject across alternating blocks of time, rather than the individual person.
It is the only way to test the impact of a structural change safely without the users cross-contaminating the physical supply of drivers.
Incredible. We've covered a massive amount of ground here today. Let's take a step back and recap this journey for you, the listener, because what looks like a simple annoyance on your screen, a high price when you are just trying to get home, is actually a breathtakingly complex technological dance.
It really is.
We are talking about dual variables, simulating supply constraints, overlaid on a global grid of hexagons. We have graph Laplacian regularization, mathematically penalizing geographic cliffs. We have predictive forecasting, anticipating crowds before they form, and switchback experiments testing it all.
Yeah.
And all of it is wrapped in psychological guardrails trying to stabilize human emotion and prevent panic cancellations in real time.
It is a marvel of modern engineering and applied microeconomics. The surge algorithm essentially acts as a giant real-time mirror. It is constantly reflecting the delicate, highly sensitive balance of our collective willingness to pay for convenience, pitted directly against a driver's willingness to earn a living.
It is a perfect, if slightly terrifying, reflection of the free market happening minute by minute, hexagon by hexagon. And that leaves us with one final provocative question for you to ponder on your own.
Oh, I like these.
If dynamic, real-time pricing is this incredibly efficient at balancing supply and demand for a 15-minute car ride, what happens when this exact same per hexagon, minute-by-minute shadow price logic expands to everything else we consume?
That is a wild thought.
Right. Imagine walking into a grocery store and the price of milk dynamically surges because 10 other people just walked into the dairy aisle. Or imagine your home electricity grid automatically surging based on hyperlocal neighborhood demand on a hot day, penalized and smoothed by an algorithm.
It could change everything.
Are we ready for our entire physical world to become a constantly shifting stock market? The next time you open that app and stare at that price multiplier, just remember, you aren't just looking at the cost of a ride. You are looking at the math that might one day run everything.